wanted to start with a warm-up that might seem like it has nothing to do with this current with calculus, I guess, but it's going to help us prepare for what a differential equation is. So it says model the following situation with an equation. The area of a circle is proportional to the square of its radius. So I want you to make an equation out of this. And we know that when there's things that are defined in calculus, we usually pick a letter to represent them. So the area of a circle, usually we say the letter A would be equivalent to that. The word is in mathematics means equals. And then proportional to the square of its radius. So I'm going to say the radius would be r, and we're saying the square of that. But proportional to means that there's some kind of constant factor, and you could call it k or c, or there's lots of different letters that are optional for that value, but some kind of constant value that would be multiplying your variable. So whatever variable is given or whatever unknown is given. So this would be an equation that models this sentence, but of course we already know from middle school math that the value of k is some constant, but specifically that the value of k is pi, right? Because we already know from middle school math that the area of a circle is pi r squared. So that would be how you write this as an equation. Okay, so what we're going to be doing is discussing differential equations. And what that is it's an equation where you have several unknown values, one of which is a derivative or a second derivative, or maybe even further, but one of your unknowns is a derivative. So here are some examples of some differential equations. Obviously, this third one is kind of a train wreck. It's just a lot of stuff going on. Really, what we're going to be dealing with are cases like case 1 and case 2. Case 3 is just really complicated. I'm just trying to show you some different variations of a differential equation. So we're going to be dealing with things like the first two. And this is my page where I remind myself to tell you not to freak out because that third example is just kind of a nightmare, but we're just going to be kind of working on the simple cases, so don't panic. So I want to start with something basic, and that is writing a differential equation. Okay, writing a differential equation. So this was also something that was in the AP review session on Wednesday, and I will tell you I've never taught my students how to do this skill separately from anything else. But after going back and watching that video, I'm finding that it's kind of important to make sure we understand the wording of what's going on. So we're going to do that in a couple of examples here. So it says, the rate of growth of a population of zombies, Z, over time is proportional to the population of zombies. And what I want you to do is just write an equation that represents this scenario. So it says the rate of growth. That means that the growth is changing, right? And change in calculus is essentially a derivative or like a slope or rate of change. Those are all the same thing in calculus. So the way I'm going to write this is I'm going to write it like a derivative. Rate of growth of a population of zombies over time. So that would be dz, the change in zombies, over the change in time, or you would say the change in zombies with respect to time. That would be our setup, and this just means the derivative of z. Is means equals, and then proportional to the population of zombies. Well, the population of zombies was the letter z, and proportional to just means there's some kind of constant value that would be multiplying that unknown. So this would be our differential equation. You could also rewrite it as, instead of dz dt, you could write it as z prime of t, like this. And then sometimes you'll even see it abbreviated further where it's not z prime of t, they just write z prime. So these are all three the same representation of the exact same thing, just different ways to do it. Okay, let's do another one. The rate of change of a level of response R with respect to the level of a stimulus S, that's supposed to be a variable, is. So I'm going to stop here. Let's write what we know so far. The rate of change of a level of response, so dr with respect to the stimulus, so ds, is means equals a joint proportionality between the level of response, which was R, and the inverse, come back to that, of the level of the stimulus, which was S. Okay, so we're going to start with this joint proportionality thing. Just means you've got two variables that are going to be in your equation. So let's start with the beginning. It says joint proportionality between the level of response. So that would be like your constant of variation multiplied by R. But then it says the inverse of the level of stimulus. So inverse is going to mean that you're going to divide by that value instead of multiplying. So this is actually a real world example called the Brentano-Stevens law. It's something that comes up in psychology. Interesting. All right, so let's do an example, a little bit more calculus-y example. So it says verify that the following equation, y equals e to the 3x minus 5x plus 7, is a solution to the differential equation below. Okay, so if you look at this equation that we're given, and if I want to know if something is a solution, typically what you'll do is plug things in and then see if it equals the value that's given. So I want to plug some stuff into this equation and see if it really does equal 0. Okay, now the two things I'm going to have to plug in are the two variables in this question, which are y double prime and y prime. Those are not given in the problem, but y is given. So I can go down here and I could easily find y prime by just taking the derivative of this equation. So let's do that. So we're going to take the derivative. The derivative of e to the 3x is e to the 3x. And that actually does have a baby, so times derivative of baby would be times 3. And then the derivative of negative 5x, it would just be negative 5. And then I think I'm going to clean that up a little bit and say, instead of e to the 3x times 3, I'm going to write it as 3e to the 3x and then minus 5. Okay, I also need y double prime. So I'm going to take the derivative again. So the derivative of 3e to the 3x would be 3e to the 3x times the derivative of baby, which would be 3. And then the derivative of negative 5 is nothing. So that would just go away. And then I'm going to clean it up again and call this instead 9e to the 3x. So what we're going to do is we're verifying that this equation, this differential equation, does equal 0. So to do that, plug in y double prime, which was 9e to the 3x, minus, and we have 3 times y prime, and y prime was, 3e to the 3x minus 5. And then minus 15, and the question is, does this equal 0? Does this equal 0? So we're going to do the math, basically just kind of algebra now. So we're distributing this negative 3, and then we'll see what happens. So when you distribute the negative 3, you get negative 9e to the 3x plus 15. Bring all the other stuff down. Does it equal 0? And then you're going to see that 9e to the 3x minus 9e to the 3x, those cancel. 15 minus 15 cancels. So this does equal 0. Okay, we've verified. And so that's all you have to do, because it just says verify that the following equation is a solution to the differential equation. Well, you've verified by plugging things in and showing that it equals 0. Okay. Here's a different application of differentials. So it says consider the differential equation dy dx equals 2 minus y over e to the x with a particular solution y equals f of x, having an initial condition y of 0 equals 1. Use the equation of the line tangent to the graph of f at the point 0, 1 in order to approximate the value of f of negative 0.2. Okay, this is a whole lot going on. Here's what we're going to do. We're going to say this. It says use the equation of the line tangent to the graph, right? We actually know that. We know, well, we know a little bit about it anyway. We know that this is dy dx. And we know that dy dx represents the slope of the tangent line. So we're being asked to find the slope of the tangent line at the point 0, 1, and then we're going to use that to approximate something different. Okay, so essentially, I'm going to draw you a really bad picture, but let's say we have this curve, okay? And we know we're trying to find the slope of the tangent line, let's say here. Ooh, you get the point. And so I want to use this tangent line to find an approximate value for something that is really close to that point. Now, is the tangent line going to be exactly going through this point? No, but it's going to be an approximation, right? It's an approximation of something that's nearby. And negative 0.2 is very close to 0 as far as x values go. So we can use it to approximate something that is very close to another value. All right, here we go. So we got dy dx, and we're going to plug in 0 for x and 1 for y, right? Because that's my ordered pair, 0, 1. So 0 is x, 1 is y. Let me make sure I do this right. 0 is x, 1 is y. Okay, so if I do the math, I'd get 1 over 1. So my slope is 1. Okay, slope is 1. And we're going to write now an equation for the tangent line, okay? Remember, this is your point slope form. Point slope. Point stroke has a nice ring to it. So you're going to use your point slope form. You're going to plug in y1. y1 is 1. Your slope, sorry, my printer started working. Interesting. Your slope is 1, and then x is 0. So we're going to write this as an equation. I'm going to kind of skip some steps and distribute and then add the 1 over kind of in my head. And I think I'm getting y equals x plus 1 for that value. So then we're going to use it to approximate f of negative 0.2. Now remember, y is the same as f of x. Guys, my printer is possessed. Sorry. So y is the same as f of x, right? That's just a different representation. So if I'm trying to find f of negative 0.2, then that just means plug negative 0.2 in for the x value and solve. And so you would get 0.8 for that value. And you're going to be doing questions like this on your Delta Math assignment for this lesson. Okay, so this example should help you tremendously for that part.